guys. So, in this section of Chapter 8, we're going to look at one of the first algorithms and basic processes that we are going to use to help us with scheduling. This is what is known as priority list scheduling, and that's going to be what we'll talk about in this section. So, what is a priority list? Well, a priority list is just a list of all of the tasks prioritized in some order, and that's the order we prefer to execute them in. So, if task X is ahead of task Y on the priority list, then obviously X gets priority over Y. And so that means that when it comes to a choice between the two, X is going to be executed before Y does. Now, if X is not ready for execution, then we skip over it and move on to the next task that's ready. And if there are no tasks that are ready after X, then the processors that we're using have to just sit and wait until one of the tasks becomes ready. So, this process of scheduling tasks using a priority list is what is known as the priority list model for scheduling. The priority list model is just a general model for scheduling. Basically, every priority list is going to produce a schedule, and any schedule can be created from some priority list. So it kind of goes back and forth. So the trick is going to be to figure out which priority list we can use, which gives us the best possible schedule. Now, we will come back to this in a couple of the later sections, 8.4 and 8.5, which we will probably take a look at sometime next week. And we'll look at some of the other ways that we can create our schedule using different priority lists to make it go more effectively. Now, there's a lot of different priority lists that you can have. In fact, the number of possible priority lists in a project consisting of m tasks is going to be m factorial. In other words, if you had a total of 3 tasks, then the number of priority lists you could have would be 3 factorial. Remember that this factorial, this exclamation point, means you multiply all the numbers that are less than or equal to the number in front of it. So that would be 3 by 2 by 1. We don't multiply by 0 or any of the negative numbers, and that would multiply to be 6. In other words, a priority list with 3 tasks would have, or a project with 3 tasks would have 6 different possible priority lists that you could use. Or if we get to some really larger numbers, like maybe not even super large, but let's say 5 tasks, by the time we get to 5, which would be 5 multiplied by 4, by 3, by 2, by 1, we get all the way up to 120 different priority lists that we can have. So you can see where the larger the project it is, the larger the number of priority lists that we can make. So we're going to try to then narrow it down to which ones are the best. So let's say that we were preparing to launch a satellite into space, and we had some last-minute checks that we needed to be performed by the onboard computers. We want to make these checks as quickly as possible, obviously for cost and safety reasons, and suppose that there are 5 things that we need to do. We've got task A, task B, task C, task D, and task E, with each of those different values being the amount of time that it would take to complete the system check. And in this case, it looks like that time is going to represent the number of hours that it would take to complete that particular check. So, in addition to knowing those, here are the precedence relations that we are going to have to consider. D has to wait until both A and B have been finished. E has to wait until C has been finished. And then here would be a picture of that using a digraph. So if you remember, we talked about digraphs in section 8.2. Here is the digraph for what that would look like with each of our tasks. So we can start with either task A, B, or C. Once A and B are done, we can do D. And once C is done, we can do E. Once both D and E are done, then we are finished. So for the first part, let's assume that we've got 2 computers which are going to carry out these tasks for us. So we've got 2 processors, which we'll call P1 and P2. So how would we use a priority list to create a schedule for those? Well, we need to start by creating that priority list. So let's say that the priority list is given by the system with checks in alphabetical order. So let's say we were going to have our priority list as follows: A, B, C, D, E. So just a simple priority list that just lists out which task we're going to do and the order we're going to do them in. So let's see how this works with our priority list model. We're going to use T to represent the amount of time that's happened in hours throughout each of the next few slides. So at time 0, at the start, we have A, B, and C, which are the only tasks ready to start. Using the priority list, where again it's in alphabetical order, we're going to give task A to our first processor and task B to our second processor. Now, at time 5, we are still working with task A, but task B is now done. Processor 2 has finished it, so it's now ready for the next available task. So remember, A is still working, B is finished. The next task would be C, and C is the only available ready task, so that's going to go ahead and be assigned to P2. All right, jump ahead an hour. So at time 6, we have just finished task A with processor 1. Processor 2, though, is still working away at task C. So D2 is now ready to be performed. We've finished both A and B now. We are now ready to assign task D. That's going to go to processor 1. Now, jumping ahead a couple more hours at time 8. Processor 1 is all the way done with D, but P2 is still busy cranking away at task C. That means that there's no task ready for P1 yet, so P1 just has to sit there idly, not doing anything. Now, at time 12, P1 is still idle. P2 has just finished C7. It took a while, but they're finally done. So both of the processors are now ready to work. They both are done with their current tasks, and now we just have one task left, which is E, which has a time of 5 hours. We're going to give that to the first processor, which is P1. That means P2 now is going to sit idly while P1 finishes, and now we are finally done at time 17. Just to give you an idea of kind of what that looks like, here would be what that schedule is. So you can see on that first idle time where P1 has to wait around while P2 finishes out C7. Once that's done, E becomes available, and it really does not matter which one you give it to. We typically will give it to the first one that's available, and that puts at our project finishing time at 17 hours. Now, I don't know about you, but looking at all of that idle time, there's 4 hours of idle time for P1 and 5 hours of idle time for P2. I feel like there might be a better way for us to do this schedule to have a little bit less idle time. In fact, let's see if we can maybe rewrite our priority list to get a little bit better schedule. So let's try reverse alphabetical order instead. Well, why would we want to do that? Why not? At this point, we're just trying some different things, and let's just see if maybe rather than going A, B, C, D, E, if we wrote our priority list E, D, C, B, A, if that would make any difference. Okay, well, let's see. At time 0, to start this thing off, only C, B, and A are able to be started. Obviously, D and E, even though they are first in the priority list, cannot be started until A, B, and C are done. So, since C is first in our priority list, so again, we cannot do E, we cannot do D. The only ones that we're able to start are C, B, and A, the first of which is C. So let's do this. C is going to go to processor 1, B is going to go to processor 2. Now, after 5 hours then, that means that processor 1 is still working with C, and processor 2 has just finished B. So now A is the only available task that's ready to go. We're going to give that to P2. All right, at time 7, P1 has just finished C7. So P2 is now busy with A6, which means that we can now assign E5. It's now a ready task. We're going to go ahead and give that to processor 1. Jumping ahead a few more hours, at time 11, we're going to have P2, which has just finished A6. P1 is still busy with E5. That means that D2 is the next available task. We're going to go ahead and give that to processor 2. And at time 12, P1 has just finished with E5. P2 still has 1 more hour to finish D2. There are no tasks left, so now processor 1 is going to have to sit idly by. And with that, here is our schedule. So we've got our schedule now. Notice that the finishing time is significantly better than it was the first time around. So in this case, we were able to go from a 17-hour finishing time to a 13-hour finishing time. In fact, it turns out that this is the optimal schedule for our 2 processors. The 2 processors would not be able to finish in less than 13 hours because there's a total of 25 hours of work, which means that even the best we could do if we were to divide it up evenly would be 12 and a half hours, but obviously they have to be whole numbers, so we can't split them. So round that up, 12 and a half rounds up to be 13. So it can pretty easily be seen that our optimal schedule is going to have to be 13 hours. Now, let's imagine instead of having 2 processors, we had 3 processors. So let's say that they wanted to get the launch scheduled a little bit quicker, so they added an additional computer to be able to do some of these tasks. So let's go ahead and use our priority list that we just did on our last example, which we did in reverse alphabetical order, so EDCBA. Okay, so at the start, once again, we have 3 tasks which are available to get started. We have C, B, and A, and this time we have 3 processors. So we're going to give C to our first processor, B to our second, and let's give A to our third processor. In other words, because we have 3 computers, all 3 of these tasks get to start all at once. Now, at time 5, we are done with one of those. Obviously, the first task, which is A, is still being worked on by processor 1. Processor 2, though, is now done with B, and processor 3 is still working away at task C. So, processor 2 is going to now pick up our task D. Or rather, is going to pick up our task, D. And in fact, we can't even do that yet, because if you remember, processor 1 is still working, so take that back. We can't even start D. We also can't start E because processor 3 is still working. So P2 has to just sit around and do nothing. Now, at time 6, processor 1 is done with A. Processor 2 has been done with B, and processor 3 is still working on C. At this point, since A and B are done, D is now available. It's going to go to the first processor that's available, which actually turns out to be processor 1, since they are, or in this case, it looks like the notes have us randomly assigning it. That's fine. We'll randomly give it to processor 2. It really doesn't matter whether you do P1 or P2. We'll just give it to 2. Okay, now at time 7, let's think about where we are at. Processor 2 is currently working on task D. It has 1 more hour to complete. Processor 1 is just sitting around because it finished A, and now processor 3 has just finished C, so we are now ready to go ahead and assign task E. Now, again, we can just do that to one of the random processors. Let's say we give it to processor 1 who's just sitting around. That means processor 3 has nothing to do. They're just going to have to sit around and wait until another task becomes available, which actually is not going to happen because at time 8, our task for D is going to be completed, and at time 12, our task for E is going to be completed, which gives us a project finishing time of 12. Now, that project finishing time is an hour quicker than it was before. In fact, you can see that whereas with 2 processors, we had 13-hour finishing time, we're able to cut that down to 12 hours, but that's really not a significant improvement. It's really the cost that you would have to think about of adding a 3rd processor for this computer system is probably not going to justify the benefit. An extra hour is probably something that you'd be willing to wait to only have to worry about 2 computers and working together rather than 3 computers. Now, this is just giving us a general sense of how a priority list works. We need to talk about some ground rules, though, of priority lists and the priority list model. So we need to define a couple of terms. We need to define what it means for a processor to either be busy or for them to be idle. We also need to define more carefully what it means for a task to be either ineligible, ready, in execution, or completed. So, depending on the combinations of these, there's going to be some different scenarios that you need to think about. Scenario number 1, all processors are busy. If that's the case, all the processors are working, there's nothing we can do but wait until one of them is finished. Scenario number 2, one of the processors is free. And if that's the case, what we should do is look at our priority list. We should look for the very first ready task in our priority list, which then we can assign to that processor. Remember that if a task is ready, then all of the tasks which are precedent to it have to be completed first. And if there aren't any ready tasks, there is nothing that's currently available, then that processor that's free is just going to have to sit around until something changes. The third possible scenario is that more than one processor is free. In this case, give the first ready task to one processor, the second ready task to the next processor, and so on. If there are more processors than there are tasks, then some of the processors are just going to have to sit around and wait for one of the tasks to become available. Now, since processors are identical and tireless, we're not going to really need to decide which one gets which. We can just choose randomly. It doesn't matter. Now, In order to keep track of things a little bit more effectively, we're going to use some notation when we are using our priority list. So when a task is ready, we're going to circle it. It says in red or just with whatever color you are working with. So when a task is ready, we circle it. When a task is currently being executed, we're going to put one slash through it. And when it's been completed, we're going to put a second slash through it. That way we are always aware of kind of what has become available. So let's talk about what that means in the context of that example we looked at the very end of 8.1, where we're building that Martian habitat unit. Now, if you remember in section 8.2, we were able to take all of those tasks and precedences and put them into a diagram. Now in 8.3, we are finally ready to start thinking about it in terms of a priority list. So let's say we have two processors and had a priority list as follows. So I've just given you this priority list for us to look at. So at the very start, we have 4 tasks which should be ready to go right from the beginning. We have AP7, so that's why that's circled. AF5, so it gets a circle. AW6, it gets a circle. And IP4, or an AD8, here gets a circle. I think that one was just off. This circle should be up here for AD8. IP4 is not ready yet, so I think the circles got off by just a little bit, so ignore this oval right here. Now, with 2 processors, what we're going to do is assign processor 1 the first task on our priority list. So that would be AD. So we would go ahead and put processor 1 here, puts a single slash through it. We are working on AD. Processor 2 then gets assigned to AW, so that goes right here. And again, we put a single slash through AW to say that we are currently working on it. So looking at those, 6 and 8 are the times. Obviously, the one that will be done first is going to be this one with a time of 6, which is processor 2. So let's look at time 6. So at time 6, we've got processor 2, which is currently done working on AW6. Now, let's see what's available. We still have AP, we still have AF. Once AW is completed, that's one of the things we need for IW to be able to become available, but we have to have IF first, and it's not open. So, at this point, processor 2 is going to go to the next task that's available in our priority list, which was AF, which had the circle. We're going to put 1 slash through it, so now P2 is working on AF. Going ahead a couple more hours. At time equals 8, processor 1 is now done with AD. Processor 2 has finished AW and is currently working on AF. The only other available task then is AP, so processor 1 is going to come up here and start working on AP. Okay, so at time 11, let's see where we are at. P2 has just finished AF5. P1 has finished AD and is currently working on AP. But that means that there's nothing available at this time. Looking at our priority list, nothing is circled. IF is the only one that's coming up, and we have to wait until AP has been finished by processor 1 before we can work on IF5. Now, once P1 completes AP, IF becomes ready. So we go ahead and circle IF. That leaves us with P1 and P2 as being idle. Or P1 and P2 are both idle at this point, so our task is going to go to P1 and P2 is going to remain idle. Now, after continuing to do this for quite a while, and you might want to try practicing it, here's the schedule that we come up with. We end up with a schedule and a project finishing time of 44 hours. Now notice that we do have some idle time in there by processor 2. Processor 1 ends up doing quite a bit more work with a finishing time of 44. Now, scheduling with priority list is really a 2-part process. Number 1, you have to pick the priority lists in some way, shape, or form. And then in 2, you're then going to use that priority list and the ground rules of that model to come up with your schedule. The first part's usually pretty quick, pretty easy. The second part's the one that's a little bit longer and tedious, mostly mechanical. We typically will use the term scheduler to describe whoever has to take on the task of the second part, whether that's a student or a machine or something else that takes the priority list and produces the schedule. So, really what it comes down to, choosing the priority list is the more important part. There's obviously a lot of priority lists out there, and only one that's going to really be optimal, or sometimes more than one, which would give the same optimal finishing time. So, how can we find that optimal priority list? Out of all those priority lists that we could possibly find, how can we know which one's going to be the best? Well, that's going to be what we'll answer in the upcoming sections. Until next time, have a good rest of your day.